Well, today we start with Professor Klaus Lehnertz, who I mean, he was here already last week, so he was the colleague who stayed on the region during the workshop. And so, Klaus, it's your floor.
Thank you. So before I start, Hilda asked me to say something to you concerning the hands-on sessions in the afternoon. Ulrike will leave tomorrow. So if anybody has questions to Ulrike, do it today. For the others, there is no strict plan. If you want to discuss with the lecturers, just come. Yeah. We are here to do that. If you have problems, we can sit together and in small groups. People that do active matter and have no idea about epilepsy and they don't want to talk about that, fine. Yeah, so just mix up whatever you are interested in and then just connect. Yeah, best time or also when the lecturers are here. As I said, we'll leave tomorrow, so if you want to do something with her, do it today. Good. Now, time and statistical approaches to detection and prediction of critical transitions. This is not an issue only related to epilepsy, but this is a topic that is quite general whenever you start to think about in terms of where do we have critical transitions in nature. Climate change, for example, we had this breakfast this morning. I take this as an example just to show what will happen if you have a non-well behaving system like the brain. Non-well behaving in the sense that we are talking about an open, non-linear, non-autonomous system, and which is much more important, it is capable of learning. So any kind of perturbation approaches that you would go in for in order to understand what is going on here might be risky. You perturb the system in order to identify something, and you probably kick it into the critical transition. In many other cases, you might even not have a model for that. And then the question remains, what can you learn about critical transitions? How can we detect them? How can we predict them? And what I will talk about today on is data-driven approaches. So you have some observations, and from these observations, you try to identify, is there a critical transition? Can I predict something? And so on and so on. Yeah. Good. Definition, what is a critical transition? A definition. This is not a general definition, this is quite broad. It is defined as an abrupt shift in the system behavior when certain parameters reach a threshold. This is the standard definition that you will probably read in many textbooks or in many papers. And it is typically that the system is then shifted into some new state, and this new state, and this is then the reason why it's called critical, is then something that has some kind of undesirable properties. There might be other transitions. Yeah, so if you take, for example, your brain, it always transits from to it. Most obvious is something like you're transiting from awake state to sleep state. You are sitting in a lecture, you are still awake. After 30 minutes, you fall asleep. This is also a transition. It might be a critical transition, not for you, not for me, maybe for somebody else. This, as I said, this is a critical aspect in many disciplines, and many people are working on that. The problem here is that we have some ideas about what would be the mechanism behind that. The most important aspect, and this is something where we also have data for that, this is bivocational induced tipping. Yeah, and then you read in many of these papers that there is something like an increase in variance and a decrease in the slowing of the system. So the system slows down, so something like critical slowing down. But there are many, many other aspects where, or many other phenomena that could also lead to a critical transition. And if you ask what time series analysis approaches do we have for all of these methods, you will find probably nothing. This is the bad news. Yeah. So we have some nice theories for that, but if you think in terms of what would be a good observation and what can I do with this observation and what can I learn from this observation by doing some kind of analysis, there's nothing so far. Yeah. Good. Next point. I mentioned this already. If we go for the system brain, and we would like to try to model that, this is probably extremely hard, not just from the sheer amount of its elements, but also what kind of functions are there observed, the interplay between structure and function, which is not fully resolved right now. And if we think in terms of what kind of networks do we have there and what kind of interactions do we have there and how can we measure that, then what we typically find is that if you study some kind of interactions in between neurons or neuronal pools, this is mostly on the level of some kind of an electromagnetic wave. And that's it. Yeah. We heard from Hinton that there are new ways of doing that in terms of some kind of chemical approaches, or you measuring temperature or some kind of assumption, so energy metabolism effectively, but that's it. What is also interesting, and this is also something that is quite often missing, is that most people only consider neurons. But there's much, much more in the brain, namely the glia cell. Yeah, and the glia is roughly a factor of 3 more than neurons. And we learned now for almost 10 years what the glia can really do. And it piece by piece, it turns out that the glia does much, much more than neurons. So in terms of information processing, in terms of being somehow involved in diseases, in the normal functioning of the brain, this is extremely important, but nobody touches upon that. We have huge fields of science. Anything starts with neuro, the neuroscience, the neurology, neurophysiology, whatever, yeah. But there is nothing that starts with glia so far. Why? We can go even further down and then ask what else is connected to the brain. And then you will find something that is probably now at the forefront. This is the connection between the gut and the brain. And if you just look at how many of these tiny elements that do some kind of processing, which is then somehow provided by bacteria that live in your gut, then you need to ask who's controlling whom. Yeah. So this is it's really complicated to understand. And if you take into account again these properties, namely that you have some adaptive system, and we think in terms of doing predictions. What will actually happen if you are successful in prediction and you modify the system with that? Then we will end up at some kind of a philosophical question, namely, can we really ever be sure that whatever we have done in terms of prediction and we have modified the system, can we really prove that our prediction is correct? Because typically what you would assume is that the system is more or less stationary or constant, but not will change upon some perturbation. Good. If you write down some equations for such a system, then you will find that everything is time dependent, which is nasty. The biggest problem here is that not just that the system is nasty, but you might have also some kind of an external forcing. You might have noise that is fed into the system, so some kind of dynamical noise, which not just changes probably the control parameters, but also the states. What you then end up with is non-stationarity. Yeah. If you think in terms of what else can be done to understand this system property, to better understand that, and how can we use some kind of a process in order to understand a non-stationary system, and you look in the prerequisites, then you will always find, we assume that the system is stationary. So at this point, go home. If you take this seriously, then you need to go home. There is nothing available so far where you can say, I have a non-state, I know I have a non-stationary system, but I'm not sure how I can do something. Then you look up what are the definitions of non-stationarity, and then you will find that it's the stochastic process. Yeah, this is the next assumption that is behind that. It's called stationary if the distribution of its states or an ensemble of realization of that process does not depend on time. Realization of an ensemble. What you're doing here is you playing with the ergodic hypothesis. You replace time averages with averages in state space. What will happen if you only have one realization of the system? In terms of the brain, you don't have many realizations of yourself unless you are not living into some multi-universe or whatever. Yeah. Then maybe. If you think in terms of initial conditions, what are your initial conditions? You have something. You start on something, it's probably a super long transient. And if you think in terms of there might be some kind of an attracting set, there is exactly one. And this is boring because this is the set that you reach when you are dead. This has nothing to do with life. So anything that we have learned so far from dynamical systems theory, in a strict sense, would be not applicable here. Still, you can do something, but you need to be aware what are the pitfalls. Yeah. So if you take this definition of stationarity, then it implies that you have anything that you measure from this distribution. So any kind of statistical moments and the joint statistical moments of some distributions of something that you have measured must be constant. Must be constant. How do you prove that? Or how do you test that? How do you test that the mean is constant? What you typically do is you take then some smaller subset of the data for which you say, I have some suspicions for which I can say this is at least approximate stationary or quasi-stationary. You come up with new names for that.
Weak stationary.
What?
Weak stationary.
Weak stationarity. Yes, thank you. Yeah. And then the next question is, how can you distinguish that one? So a non-stationary process with the dynamics where you have changing parameters, where you have a driven system. And if you have only transient dynamics, how to do that? Yeah. Whenever you have done lab courses, you always assume that you have stationarity, because otherwise there is no guarantee that you have a reproducibility of an experiment. And then you run the experiment and you do it 100 times, and then you go for the law of large numbers, and then you assume, aha, now I have something. Good. You can do that if you think, or if you have set up your experiment such that you can guarantee at least a little bit of weak stationarity. Good, approximate, whatever. Yeah. Then you can switch between phase space ensembles or time averages. This is the only way you can do that. Another issue here is what are important timescales? What is a timescale that you think is important for your system? It depends on what you measure. It depends on what you look at. It depends on what you want to do. We talked already about the EEG, and what most people are looking at are rhythms. Because if you take a textbook on neurophysiology or electrophysiology, you will find that the EEG is defined by blah, 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 and these are only rhythms and some predefined frequency bands. What else? The whole work behind that. And this is 1/f like noise. In quotes. Yeah, it is of course not noise, it has something. But it's a 1/f like signal. What is an important time scale there? Something between something and something. Yeah, between 0 and infinity. These are the important time scales. you need to fix something. You need to fix that, and this is then something where you need also to, when you do the measurement, be aware that whenever you choose filter settings, if you try to restrict the bandwidth of your signal, irrespective of some signal acquisition aspects, you restrict your signal such that you can make some claims on timescales on whatever is relevant only in that frequency band. And that also then defines your timescales. And that's it. Yeah. If you have short timescales, and this is then exactly the point what people are then doing, then you can come up and say, okay, given that, I can approximate my system station, or weak station, or approximate station, or whatever in that. So, and then if you go to longer timescales, and now depending on where does this non-stationarity come from, is it an intrinsic effect? Is this due to this, that the system is being driven, due to noise, whatever is the reason for that? On these long timescales, you might get much more information about these slowly changing control parameters due to some kind of external driving force. So there is some kind of a balance that you would need to make in order to distinguish different aspects of what do you really want to understand from the dynamics, what are the timescales that you concentrate on, and then this balance between stationarity and non-stationarity. This is then your choice. Good. Here's one stationary signal. Which one is that? Any idea?
Blue one.
The blue one. Why?
The other are not stationary. No,
Any idea?
the one, yes, the pitch.
This one? This is a chirp. There's a change in frequency. This is highly non-stationary. Okay.
Maybe that's the ETG sometime.
Yeah.
No, that ETG like
The ECG.
yeah, that's after another it's after the time of the rating point.
On the right one.
Yeah,
Sure. But I want to include the transition. We're talking about transition.
it's after the transition.
After the transition might be. Okay. So you try Klaus. The same me. You know what this is? Random numbers drawing from some distribution with the deviation off and the standard deviation off by a construction station. Anything else is, and you know that data. This is the temperature rise. This is an earthquake. The red one is a seizure. This is pressure changes during some neurological event. Sure, this is also some kind of an artificial signal, but this is something that you can hear outside when the birds sing. Yeah, so everything is non-safe except for something that we have generated. How do you cope with that? Many ways to do that. And what you typically find in many disciplines is probing. We don't talk about the ongoing dynamics, but we are only looking for some input-output function. You perturb the system, let it relax, and from the relaxation phenomena, you get some idea about what the system will be doing. Could be risky. Yeah. And then you stick again to ergodic hypothesis. You do this many times, and then you take an average and you place this time average then by an average in the state space, and then you are done. Well, then you can make some claims about invariant measure. Good. If it's risky, you need to observe then the system over long times in order to capture all the relevant timescales. Or you say, I only restrict myself to some timescales, and I know that there is something else in the background, but I omit that. I don't have access to that. Good. And then you do segmentation. You segment your data. That could be Again, according to some rules that you set up. Yeah, this is again weak stationarity. You would like to have with an overlap, without an overlap. You are not interested in, because depending on what you do later on, that might introduce some kind of strange correlations that only come from the segmentation process. Yeah. And you need to build some kind of an accuracy. Whenever you do something with the data, whatever you estimate from the data, you typically have something, some definition of something, be it the mean, be it the variance, be it the correlation dimension, the Lyapunov exponent, whatever you are doing there, you typically take an average. And these averages are again defined in the limits, n large. If you don't have that, you have an error. Something that you would need to take into account when you do the segmentation. So the number of data points define your accuracy, but they contradict the requirement for stationarity. This is then the balance that you would need to make in order to have something where you can say, given the setting, given this data, given my approach that I would like to do, I would like to understand critical transition. I take this technique, or I take a mixture of different techniques. If you do machine learning and you do a mixture of different techniques, take into account that they all have different requirements. You might find something that wins just because it's a little bit more insensitive to the number of data points. You should check that. If you go into state space representations of the data, there's one nice technique that has been proposed by Rainer Egger and others called over-embedding. You embed your dynamics in state space, but not as usual, taking into account the Whitney theorem or the weak Whitney theorem, but you do include a little bit more dimensions according to the different non-stationarities that you have. You consider each of that as an independent source of information or an independent degree of freedom that you need to add in order to set up a better state space. Again, that sounds great. Take into account whenever you try to embed data, you would need to have a sufficient amount of data that helps you to understand identifying the underlying structures that you are interested in. If not, it's risky. So then, many techniques. There's one technique that is also based on the recurrence quantification analysis, which is typically some kind of a loss of recurrence. So some kind of patterns that recur in state space are lost due to non-stationarities. And then you need to revert thinking and say, I'm not interested in understanding the recurrences, but why is there a loss? And how can I quantify this loss? And then from that point of view, you go away from the binary decision, stationary or not, but how non-stationary is the system? Some kind of a quantification of non-stationarity. This is something that is rare because most people don't look at that. They only want to know if the system is stationary or not. But you might also learn something from the non-stationarity. Yeah. That could be an interesting aspect of dynamics. Good. Let's assume some kind of an experimental situation. Yeah. So you have a system. You have no idea about the system. You have a name for that. You don't know what is relevant. You don't know the relevant timescales. You don't know relevant observables. You have done some measurement, or somebody else has done some measurement. What can you learn about that? Or what do you need to take into account in order to go into the direction of I can identify critical transitions? The first one that you would need to do is you need to make up your mind, is this really a good observable? Is it just one? Do you need more? Is it doable to understand critical transitions just from having one observable? And even if that was only a projection, is this a good projection? If you ask experimentalists, is this a good observable? You said what? We have measured that. But Thank you. Many other requirements that you typically don't come up with. Yeah, so if you do analysis and you ask to go for the people that do the recordings, you have in mind what you would like to do. Don't expect that they know what you do. Yeah, and they don't even might not even know that you know that they make some pitfalls and make some errors, and you tell them how to do that. Then you run into the problem that they will probably say, sorry, this is our setup. This is the way we do it, and we did this already the last 150,000 years. And we don't change that. Never change a running system. This is then the argument that you get. You have a system, and now you ask how to sample that. We take another, again, the climate system. How do you sample climate in space? Where do you place sensors? And how? Any idea? How is this done?
Meteorological stations. Meteorological stations.
And why?
Easy, quickly.
Easy. What else? Simplest assumption. It is always the simplest assumption. I will tell you in the next lecture on Friday what that can lead if you do it like that. There are, of course, theories that you can use. What is a good sampling rate for chaos? Any idea? These are the questions that you would need to ask. And you also need to discuss with the experimentalists. Yeah. If you have the suspicion that whatever you are interested in comes from a transition from fast slow dynamics to whatever, you would need to have a good sampling. Otherwise, you will not see that. If you have a fast slow system and you only concentrate on the slow dynamics, but not on the fast dynamics, because your sampling is too shitty, yeah, forget it. You will not see it. All the theories that you know from textbooks, like with Shannon and so on, are made for linear systems, but not for nonlinear systems. Okay, how to proceed with that? Once you have made up your mind of what is a good observable, then you need to go for probing or observing, because then you define your timescales. If you do the observation and your system lives long enough and you have enough PhD students that can survive for the next 100,000 years, then you can probably observe something. Yeah, good. If not, short-term relaxation phenomena. This is what you typically do. Yeah, but this is then you're only looking for transients. Who tells you that the transient dynamics is the same, has the same ingredients, has the same characteristics than the long-term dynamics? It's an assumption. Yeah. And then you do some kind of experiments, and then you say, yeah, that captures almost everything that I would need, including critical transitions. Probably not. Yeah. Okay. If you are faced with this issue of non-stationarities, and you decide you do some kind of segmentation process, what is then a good segment length? Yeah. Now we end up again with the same question about accuracy. Can I do something like defining weak criterion for, or an approximate criterion for, whatever you want? Yeah. So you see already in the background, before you have done anything, you need to make up your mind that there are many, many aspects that you need to take into consideration up to the point that you say, now I can start my analysis. Yeah. And already at that point, there are many people that say, sorry, this is not the data that I can use because it does not work. I know it will not work. Yeah. Another aspect that also attaches directly to the measurement. The precision of measurement, not just in time, but also in the amplitude range. You go to the supermarket and buy an AD converter that gives you 64 bit for 50 euro. Okay, take 10 of them. Yeah. Who has that? If you ask people what is the precision of your measurements that you have? From 2, but not 64. It goes from 6 to maybe 20 or 30 in best case. What kind of noise do you have? Standard approximation is white noise. What does this mean? You are simulating measurement errors. You are simulating your what is this? I'm sorry, I'm looking for the word for that. You are not capable of doing the perfect measurement. You have some kind of an uncertainty just because you do an experiment. Good. What else? What about environmental noise? What about interactions between the heat bath that you are living in or your system is living in with the system? What kind of noise is that? I use that term here. Yeah. In whatever kind of equations that you have, you say I have a deterministic part plus a stochastic part. Why plus? Why is it always additive? Well, it's not multiplicative. Why does the noise not feed into the dynamics? What will happen if you do that? Then you will realize that there are not many approaches that can do that. And even if you find some approaches based on the Fokker-Planck equation or the Kramers-Moyal extension, doesn't matter what it is, you always assume additivity. At least you can decompose this up to some point. Up to some point, yeah. But anything else is not captured here. And there still might be some kind of an uncertainties. How do you model that? How do you account for that if you do real-world measurements? Put everything into white noise? Could work, but not necessary. So, critical transitions again. You set up an experiment or you do an observation and you would like to find a critical transition. You would like to characterize that. If you have no idea what a critical transition is and how to distinguish that from non-critical transitions, because the system undergoes any kind of transitions, and there's only maybe one critical. Yeah, you do the experiments and you hope that there's at least one. Keep this in mind. The number 1, we have one extreme event, one of these critical events. Later on, we will need to do statistics based on a huge number of any events against 1. We set up distributions and characterize distributions from one event. Yeah. Take this into account. If you have more events, you capture more events. Are you sure that these events are always the same? Can you be sure that the transitions into these are always the same? You can. This is what many people do. You have some baseline that you define as this is the constant dynamics, this is the normal dynamics, and from that I see a transition. What will happen if this fluctuates? You have something that fluctuates and goes into a critical transition. This would be the scenario that you would need to take into account if you would like to do it perfect. Good. You place your sensors again. You have chosen your sensors already, maybe not for detecting the critical transitions, but because you have observed something else based on some knowledge. Maybe. Then you observe the system. And then you know from physics the observer problem. What will happen that you just due to the observation, you have changed the system. Can you really be sure that what you have observed is the dynamics, the eigendynamics of the system, and not whole rumborium that you have done in order to observe something. This is what you would need to take into account. If you typically you fix everything, you fix the recording process. You would not go and you see a transition from some kind of a slow changing dynamics into a fast chaos, and then you say, now I have to adopt my ADC and my sampling rate. No, never. Because you don't know when this will happen. So what you typically do is then set everything such that you have an oversampling in space and time. Bandwidth is such that you can say, I have captured really all relevant time scales. Yeah. And then this event does not happen. And what you have is an over-representation of your data with lots of correlations in the data.
Or a lot of data that you cannot manage with your computer.
Yes, yes, yes. What is adequate sampling? Again, in order to avoid misinterpretations. And this is also an aspect for prediction. If it's the first time that you do a prediction, you have no idea that this event, or if you have no data for a similar event or for exactly that event happened before, you don't know what is going on. You would really do prediction. You would need to set all these aspects before you do something. So and then, if you want to distinguish something, you would need to record enough non-critical and critical dynamics. As I said, the worst case is just one. Best case is as much as possible. Yeah, under the assumption that this as much as possible is always the same. And the normal non-critical one should also be good represented because, as I said, you come from a spectrum of dynamics and you go via some transition into a subset of that. That is a little bit different, but that's what Mari said. You sample and sample and sample. Yeah, and then you realize I don't need that. Okay, then you say, I take only snippets of the data. Because the rest is, for some reasons, too noisy, I don't need that, because it was Friday, whatever the reason is. Yeah. And then you reconstruct something from the snippets. How do you need to choose your snippets? According to some criteria. How are these snippets arranged in time? The magic word behind this is unevenly sampled data. You can extend that now to unevenly sampled snippets. Simple example, do a Fourier transform of unevenly sampled data. You go to astrophysics and you know that there's a long scalar parallelogram with which you can do something. How to do that in space? Any idea? Have you seen something like that before? Now you combine it and do it in space-time.
You pass by the Kriging correlation, and then you transform the spectrum.
And what will happen if the underlying dynamics is exactly that, the decreasing correlation? Yeah. It's just a caveat. Yeah. It can happen that whatever you identify is due to the choice of the snippets. I haven't seen these studies right now where people have shown that if you have a continuous recording, you take out randomly some snippets and then try to reconstruct the dynamics again, the relevant aspects of that. And I bet you if you do that, you will see that there's lots of misinterpretation in the page. So that if you are not yet with the analysis, now this is just prerequisites. You need to decide next, what do you want to really do? Detection, prediction, combined, whatever you want to do. Yeah, means whenever you go for, let's say, detection, you do some kind of an offline analysis, you have the data, you would like to learn something about the system, you go back and choose the data and say, okay, offline is only detection. Online would be from the data stream, you continue, and you do probably some kind of a prediction with that. Yeah, sometimes you try other terms. This is then called a retrospective or prospective analysis. Retrospective offline, prospective online. And then depending on what you want to do, you can also do detection online if you want. Yeah, but this is some kind of setup that can be used in that sense. So now, what do you want to analyze? What is the characteristic that you are interested in? You go to textbooks on time series analysis. Good. The first distinction that you find is linear, nonlinear. The second distinction is univariate, bivariate. The third distinction is, oh, we can also include multivariate. And then you realize that this is probably not sufficient. I would need more. Random matrix theory. Why not? Why not go back to nuclear physics and use this old stuff again? Well, there's so many nice things to do. Then comes complex networks. Why not writing something like the clustering coefficient of a time series? Whatever you are interested in. Yeah, it depends on the questions that you ask. It depends on what you want to analyze. And then you choose your time series analysis techniques. It's your choice. Or you have some kind of specific idea of, I can identify something because of. Yeah. If you don't know it, try and error. Yeah. The next aspect is you need to interpret something. You do the analysis, you go back to this speciality, the climate people, and say, whenever I see a change of the assortativity coefficient, and it goes in the direction of disortativity, then I know that this will be an indication for a climate change. Okay. This is the interpretation coming from the time series analysis. Now you need to translate that into this language of this speciality.
And if you work with neurologists, it's even worse.
Yes. Okay, I know. I try as broad as possible and not go into this field. And what is the physical mechanism behind that? What do you learn from? I mean, I showed you some possible ideas about what would be the underlying critical, what would be the mechanism for this critical transition. What do you learn from that? Yeah. If you know, if you have a model, you can go for all these different types of transitory mechanisms. You have your observation, you have your, I mean, observables, yeah, not just some data. You have your observables, you know what you do, you know these time series analysis can give me, if the output of this analysis is in a given range, then I know that this is the mechanism. You can try to look at this up in the literature, you won't find that. It's not available yet. I know that people are working on that, but that's it. You fixed your time series analysis approach. Now you do it. Then you see, oh, I have to do this and this and this and this and this. All these algorithmic parameter settings, some pre-processing steps, the analysis parameters, the windowing, probably some kind of a filtering, and so on and so on. That needs to be fixed beforehand. If not, if you adjust everything, then you see at the output the adjustment of your parameters. You can do that. You have learned nothing. Yeah. You can also then use some kind of a noisy input and do exactly the same, then you will also see the same findings. That has nothing to do with the real world system. Yeah, but it can happen. You have done that. If you use, now we are still talking about non-stationary systems, what you will then end up is some value, some number as an output of your analysis for that window. Then you go for the next, and the next, and the next. So you move forward in time, forward in space, whatever. Yeah. That means you end up with a new time series. You can interpret that as some kind of a reduction of the information content of the original data. Okay. We have a new time series. And then you can do again time series analysis of a time series until you have reduced to 42. Then you're done. Or you take this time series and then you try to detect something on this time series. So it's some kind of a compression of the original data to something that you deem relevant for this dynamical system. Then you try to identify, is there some kind of an indicator for critical transition or whatever. Yeah. So you do then some kind of statistical analysis for performance evaluation and so on. Okay, this is what I just mentioned. Choose this from that field, what is available. Yeah, we can go into these details if you want. In the hands-on sessions, I can tell you more about it. It will not touch upon this because this is at least 2 years lectures. Yeah. At the end, this is at the end, you go up for some classification. Critical or not. Yeah. Means you need to distinguish 2 types of data. So some distributions that you have. Find the discriminant functions. Best case, line. Worst case, some polynomial. Or you have some machine that doesn't know. If you don't know textbooks of mathematical functions or whatever. Good. Outcome. Yeah. The time on the x-axis. I know there was a critical transition because I have observed a system. On the other hand, there's the red line. Critical transition. And I've seen that there are also other non-critical transitions. The system has made something. So whatever is shown on the top is the truth. Now you have some observation. Something like that. And now you ask, can I detect that? Can I detect these transitions? Again, what we do now is again some kind of a time series analysis approach or some statistics in order to identify changes. That comes under the umbrella of change point detection. Yeah. Change point detection is also anomaly detection to identify times when the probability distribution from statistical moments, correlation, spectral density, whatever, of a time series changes. So you can also go back to your original time series and do it there, but we are now already on the level where we have some reduction of information. How do you estimate statistical moments? Can you estimate the mean from 2 data points? Can you estimate standard deviation from 2 data points? No. Useless, but always.
I mean, you can get a number.
Sure. Just an example. Yeah. This is exactly what people have done in the early days of seizure prediction. Yeah. You have an event, you take the data before, and then you see that there's a change. Then there's a change during the seizure, and then there's a change probably prior to the seizure. Prior, if you look at time scales, here we have something like minutes. Here we have something like minutes. Here we have window numbers. Here we have again minutes. Sometimes you have seconds, sometimes you have frames. Some statement about some time. Yeah, you can refer this to real time or not. If you know what this has been done, then you see something. And then you see that there's a change. And then you say, ah, done. Now I see a change. This is the critical transition. Good. You can leave it as it is. This is what you also find in many other fields. Also in climate science, in the earth sciences, people don't have continuous observations. They restrict the event, plus minus, and then they're saying, okay, there's something. Not knowing what is going on elsewhere. Yeah. We come into that point. If you have something like that, critical transition, non-critical, whatever you have, CP means your detector, your time series analysis said, here's something. You have identified a change point. Yeah. So how do you interpret that? This is nasty because the change point detection is after the critical transition. Football, soccer game fans, they would say, so this is today's, tomorrow's yesterday. Not an issue. Yeah. Before the seizure is after the seizure, and after the seizure is before the seizure, it's the same. Good. They coincide. Like here. And here. Yeah, you have some technique that allows you to detect a change point, but you can't really distinguish between critical or non-critical. Good. Why? My time series analysis technique is not sufficient for that. Possible interpretation. You precede a critical transition. This is exactly what you want. Now I have it. Yeah. Now I know that I can predict something. Now comes already the question, how often does this happen? How often does the other happen? How often does the other happen? And so on and so on. So you look for true predictions, false predictions, don't know that direction, don't know that direction. You would need to have some good statistics to identify what is going on what and how to interpret that. Yeah.
But shouldn't you try to find some robust parameters that you look at that they remain there when you have the transition, but if it's not a transition, they disappear somehow?
This is defined a game builder. Here define robustness. I come back to that. Let's go one step before. Here, I have an event. And I say, this is the critical transition. How long is a critical transition? Here you have something that happens. Let's assume here is the beginning of a seizure. Here's an earthquake. Whatever will happen. Where's the critical transition now? If you would like to identify a precursor, yeah, then you would probably say the critical transition is here. Because then you have some kind of a transitory phase that then ends up into something. If you place it here, you have a detector of this event. So no predict. You need to choose what you want. Yeah, and this is also then the definition of what is actually the onset of the critical transition. Is this some kind of a phase? Is this just an event in time? So the rock. Or does it have some extension? You can also do the same in space if you. Yeah. You have that. If you have some kind of a phase, then it's not just a distinction between discrete events. Now, you would also take into account that you have phases that have some duration, and you would need to distinguish such a phase from other phases where you see some kind of changes. This depends on what you want to do with that. Yeah, but you need to take that into account such that you can distinguish these phases. So change point detection is a single event. And now we come to the critical question of the transitory phase is the critical dynamics. How can we distinguish that from other non-critical dynamics that also have some kind of extension, space or time? Yeah.
In your experience, usually critical transitions have a stable period of time, or usually they vary.
Good question. Taking that, let them vary. Yeah. If you fix that, yeah, you have one observation, you have the transition to this undesired state here. You choose that one retrospectively as the duration, but you know it only happens here. If you then try to distinguish this from something else, you might fail. If you take it longer than that, you include something from the non-critical or from the normal dynamics, you might fail again. Your choice.
You will always fail.
No, no. The point is, if you do this introspective, if you do this in some kind of prospective sense, you do it in an online stream, then you probably need to fix these parameters. Yes. Unless you say, okay, there's again a change point detection, some threshold detection. If that works, it's fine. Yeah, but usually it does not work. Yeah. So allow variability in time or in space, and try to adopt that as best as possible. I will show you some ways of how to do that. Takes a little bit more computation, but it's doable. You know this paper? Famous. Number of citations, several thousand, I don't know. There's one example. This is immediately in the first sentences. Yeah, blah, 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 or epileptic seizures. Which is based on an observation. In that one here, adapted by permission from, and this is copyright 2003, and that comes from the group Paris. Jack and others. Yeah. Well, they have shown that there is something before. You look again on the time scales, we are talking here about seconds. And there's only the event, here's the seizure onset, maybe something declines later on. And we're talking about that one. But one specific point here, you need to rely on the onset of the seizure. You ask a clinician, here's the recording, where does the seizure start? The minutes of contemplation, there. Okay, we go to another one, same story, there. Inter-rater uncertainty is, Christian, correct me if I'm wrong, 10 seconds would be 10 seconds. So we are talking here about, this is 200, this is 100, this one here, this increase would already be seizure. Who knows? No clear-cut definition. You need to allow variability. Yeah, not just in the duration, but also on the transition, when it will happen. Yeah, make it a little bit fuzzy, taking into account the uncertainties. That was based on something where Paris group and then also other people have shown that do we need that? Do we need all these nonlinear batteries? Do we need dimensions? Do we need, what do we need? Yeah. And that was just to show simple correlation measurements also makes some contribution to that. And only because it was correlation, Jeffer group hopped onto that and said, here we have an indication for critical slowing down. During that time when that was published, the term was not there. It came later. But here we have some indication and we see, and this is why it works. Yeah. Is it the uncertainty in defining something, or is there really an indication for something? Yeah, this is the problem. We assume that there is some kind of a transitory phase. We know we define the end and the onset and the offset. We know it wobbles around. Then you do some statistics and find, now it works. Yeah. This is lying with statistics. That's another example here that was done by one of my bachelor students. She used, I don't know how many seizures, from 28 subjects, 2,000 hours of EEG recordings, 105 seizures. To see, can we identify critical slowing down under the assumption that prior to seizure there is a transitory phase that has a duration of And we do this for each and every recording site. And we would like to identify is the critical slowing down, and critical slowing down in the sense that the variance goes up and the autocorrelation declines. Pathwise theory relates statistical moments to the power. It's the same. Variance, autocorrelation function, linear theorem, everything is the same. It's just a transformation from one domain into the other. People consider this as independent markers. Yeah. 2 times shit does not give you no shit. Some exemplary evolutions, here are seizures. Whenever you have a red line, then increase, then decrease, you zoom in, and 4 hours before, 4 hours after. So this is now triggered onto the seizure. What do you observe? Then increases, then decrease, then no change. Something. We do statistics, check the robustness. If you believe that a deviation from the receiver, we come back to receiver operating characteristics, in the 16th digit after the comma from 0.5 is an indicator for a critical transition, then we found it in 1 subject in 1 recording site.
With the critical patient. The critical patient.
Yes. The critical brain region. People have observed that not only in the brain, but you can come up with alternatives. This is called critical speeding up. Of course. So what system produces critical slowing down, critical speeding up, critical no change, critical some change, critical undefined, whatever you want. And what is the mechanism behind it? Yeah, if you use bifurcation, use tipping, you expect something. Can you also expect the opposite of that? Good. I mentioned receiver operating characteristics. This is 5 days of record, 5 days, almost 6 days of recordings. Whenever you have here some red line, again, there's a seizure, and now we assume that here's some change prior to the seizure. This is now in the order of 4 hours. And I would like to know, does this deviate from the rest of the world? Whenever I have something before the seizure. What do we else see is this fluctuation? So this bluish one is assumed to be the normal. We moved a little bit of the part after the seizure because that might be some kind of strange kind of dynamics. In order to not confuse the detecting scheme, we left that out. Yeah, good. You have 2 distributions of data, the blue one, the red one. You have distributions of data, and now you ask, can I distinguish them? Then you see by eye, yes, that works. Yeah, and then you do receiver operating characteristics, so you ask for robustness in terms of sensitivity, specificity, true negative, false negative, true positive, false positive, whatever can be done from detector theory. Then you see, oh, area below the curve, 0.8. Done. Yeah. This profile that you see up there, this is based on synchronization measurements, phase synchronization between different brain regions. And we have selected for that one out of 128 by 128 halves. So many, we have chosen 1 because that showed exactly what we would like to see for didactical reasons, of course. Yeah, there are many, many others where you don't see that or you see exactly the opposite. How do you interpret that? You are at this point. You only stay here and say, now, I have done what statistics would require in order to define something that is robust, and now you need to interpret it. Good. We see receiver operating characteristics 0.8. Good. Yeah, this by definition, this is the almost the best. Yeah, you are not in the upper left corner, you are not one, nobody expects it for biological data. 0.8 and higher is perfect. Good. So you have detected the critical transitory phase. Is correct. Under all the assumptions that I made before, and given that I was correct, then I can probably make some statement in that direction. No. The time series analysis techniques that I used allows me to interpret the critical dynamics. Good. Now you go and say, because I've seen that, phase synchronization is a method to identify critical transitions. I said that, believe me.
Professor Lehnertz.
No. So, and it can help to derive better models. So people run in the direction of, I try to identify with whatever kind of tipping, I now need to combine it with phase synchronization, and then I'm done. Then I explain the word. Spooky or not? I'm only quoting from the literature here. You can also put the other way around and say, because it's not one, the methodology is wrong, the statistics insufficient. And then, what would you trust? Good or not? Who's for good? Who's for not? Who says good? Mario, one. Who says not good? Nobody. Undecided.
No one.
The rest, okay, good.
Uncertainty principle.
Let's assume we end up with a receiver operating area under the curve of 0.50000, many zeros, 1. Yeah? Point. Yeah, not below the diagonal, but above. Cannot be detected. Could be wrong assumptions. Duration, wobbling not correct, whatever. Yeah. The other one, deviation from the one, probably not correct. What is the correct one? Too many assumptions here. Yeah. Insufficient methodology, insufficient statistics, the same as above. So now, build up robustness. This is where most work stops. Receiver operating characteristics. Because this is defined as the robust measure. And then we need to test the quality and reliability of detections. Good. A little course in statistics do that. Little one. Very little. The simplest answer is you compare the distributions that you had. Now we come back to what I said in the beginning. Remind the number of critical transitions that we have. Worst case was 1. Yeah. And we have the rest. Now you set up the distributions. So you have one distribution that does not contain any critical transition. This is well sampled. And you have one single event. And now you compare the distributions via some Gaussian assumption or non-Gaussian assumptions. Is everything is Gaussian distributed here? Have you checked that? What is the distribution of all phase synchronization measures in the world and the universe? You know that? Is this Gaussian distributed? What's the distribution of all Lyapunov exponents from all dynamical systems that live in the universe? I have no idea. Yeah. Is the Gaussian assumption correct? This is what you find in many toolboxes. Because it's so easy. Make up your mind that this is probably not valid. You have some tests for the comparing means. You have some tests for comparing, no, you have a test for comparing the variance under the Gaussian assumption. I know that there is something like squared rank tests for non-Gaussian distributed data. No idea if this. What about higher order? What about skewness? What about kurtosis?
You don't care about it.
Huh?
You don't care about it in the
You don't, why not?
Because
Many of these phenomena show up in the higher order moments. This is the point.
especially experiments.
So if you ask this statisticians, is there something for the skewness for non-Gaussian distributed data? Maybe not. Please look that up and let me know if you find something.
Maybe not skewed to 60.
You use these tests here, the prerequisites for that, for the usage of these tests. Yeah. Each data is independently sampled from some distribution. Implication for that is no memory, no dynamics. Time is not important, stationarity. Now, simple ansatz. Yeah, might make sense, but be aware that the prerequisites kills everything. And you need to again make many assumptions. Now we come back to receiver operating characteristics. Yeah, not just I compare the distributions, but let's look at what else can we learn about that. Yeah. So we define sensitivity, specificity, false positive and false negatives. Identifications of, now again, critical transition, critical phase, whatever you have in your distributions. Sensitivity means that you have the probability of a positive test. So your test statistics tells you this is a critical transition. And it was followed by that. You have identified it. Good. Specificity is exactly the opposite. You need to take into account that you have a negative test, namely that your test statistics tells you it was not a critical transition. And it is correct. You have identified a non-critical transition and you know it was not followed by something. Good. Then you need to have the mixtures. Critical, incorrectly identified as non-critical, and non-critical, incorrectly identified as critical. And then you find in textbooks all these nice pictures here where you have now two distributions, and then you say, okay, this is the true negative, this is true positive, wherever you have this overlap, this is then false positive, false negative, and then you can compare sensitivity, specificity. Worst case scenario, 1 point here. Interpretation is always like that. It is graphically, or you reduce that to some area under the curve or whatever. You plot the false positive rate against the true positive rate, or sensitivity versus 1 minus specificity. Then the same. The main diagonal is a random detector, random classifier, and the best one would be up here. Anything else is then, if it's positive or negative, depending on how you define that, could be some kind of increase, some kind of decrease of something, but it gives you an indication that something has changed. Yeah, good. And then either you find plots like that, or you take the area under the full curve or relative to the random classifier, and this is then the definition of robustness. How reliable are we? Good. I showed you this already before. It was from the first seizure prediction conference. Just to show what can be done. Variance, skewness, kurtosis, statistical moments of the EG in some frequency band. Now frequency band. Delta, theta, alpha, beta, gamma. statistical moments of the power spectrum, the decay of the autocorrelation function, the correlation dimension, the surrogate corrected correlation dimension, Lyapunov exponent, surrogate corrected maximum Lyapunov exponent, a measure for the loss of recurrence, some non-stationarity criterion. This is an algorithmic complexity that is based on synchronization of the EEG, and then you estimate some complexity. Again, some loss of recurrence here. Then we use the maximum of the cross-correlation function, and here we have now phase synchronization measures based where you estimate the phases from the Dirichlet transform, from the wavelet transform, and some other measures for nonlinear interdependence. So generalized synchronization, phase synchronization, linear, nonlinear, whatever you want. The same data, the same approach, you let it vary. You assume that the duration can vary between 5 minutes and 4 hours. Find the best, such that you can make up some claims about this is robust. You find the best. Here's also some thresholding. Yeah. How many percent do we allow as an uncertainty if something changes? How well defined is that? And this is now the ROC values. So now you need to interpret numbers again. Which one is better?
It's in the bivariate. But I mean, at this I think it's quite fair because you're trying to see multiple data in order to take some conclusion. It's better than you just go, I'm going to make a maneuver, for example, and that's all.
Yes, good. Interpretation.
Yeah.
Interpretation. How do you interpret that now? Well, given your time series analysis approach, we are still under the assumption we would like to characterize critical transitions. You have a whole battery of techniques that have any kind of speciality, linear, nonlinear, bivariate, univariate, from dynamical system theory, just pure statistics. They allow you to do some kind of an interpretation. What has changed? Going back to the mechanisms. Yeah. Any idea?
Well, it probably means your signal is not enough to inform you.
To the observer. Could be. Yes. Spatial sampling, temporal sampling, filter settings, observable, whatever. Yeah. This good that you say that. Yeah. That needs to go, everything needs to go into this interpretation again. Here's something shown in red. I will come back to that.
How those, I mean, fluctuations that you have in your data, I mean, when you compare to the fluctuations of the moment, for instance, of the seizure, that is, as you were saying, is someone who comes and has to tell you starting the
Yeah.
I mean,
Okay, there's some fluctuation. Good. Yeah.
yeah.
Here's something that is more or less constant.
Yeah.
And then it starts fluctuating. Okay. You have a little bit of idea about during the clinical setup is being done, they reduce medication. Then it goes up and then it goes down again. We are humans. We are living on Earth. We are probably affected by 2 large planets, the sun and the moon. Circadian biological rhythms, other biological rhythms. This is everything that you can see here. Yeah. What you say fluctuations. Yeah. This is the fluctuation being induced by drivers, external drivers. You would need to take that into account. Yeah. So whenever you see now, does it go down or does it go up? When the event, you have something that oscillates with some strange period in the background, and you have an event that is on the descending part and something that is on the ascending part, all these fixing of parameters does not make sense anymore. This is unfortunate. Yeah, but this is where we live, yeah.
And the person may not even be there when he starts.
Yes.
It's a machine. Oh.
After that conference, we had some conferences where people used shared data. Then there were contests. Also with machine learning, people set up machine learning algorithms just to see what is good. First one was, if you look at here, the receiver operating characteristics between 0.78 and 0.82.
Sorry, these are the same data sets? These are the same data sets?
Data set. Yeah, shared data. Everything was the same. You use your algorithm, you use your setup, you combine whatever you want to do something. So I have no idea what this is. Yeah. What I wanted to show you. How many digits after the comma do you believe for such data? So 0.8. Yeah. This was then the second one. We have 5 digits after the comma. What does this mean? Is this really a reliable estimation of predictability or detectability? Yeah, this comes from it is the best that you can get from statistics. Yeah, so far. But it does not tell you anything. So if you wrap that up, receiver operating characteristics, area under the curve measures plus derivatives of that are not reliable measures for quality. This is not a good robustness estimate. Yeah, not if you just take it in that sense. Because this is the main prerequisite that you have. You need to have balanced distributions. Balanced distributions means the number of entries that you have in each of these distributions is comparable. Not 1 against 10 billions, but 10 millions against 9 billions, for example. For single events, then even if you have only rare events, and this is if you do critical transition in terms of detecting or identifying extreme events, you have exactly that problem because extreme events are defined as rare events. So one of these distributions is not, it's underpopulated. Yeah.
What do you think of other measures such as F1 scores or Matthew's correlation coefficient?
You can continue with that. It's exactly the same. I show you something else. This is what Hilda said. The fluctuations that we would need to be taken into account. Yeah. People use, for example, climate Breyer score. Yeah. You take into account many other aspects in order to again distinguish distributions. Yeah. The prerequisite is always balanced. It's not there. F1, Breyer, whatever you take, always end up with that one. Some people claim that Cindy, compressed sensing, whatever is that this is better. Yeah, I haven't seen that it's really better yet. This is too early, probably. Yeah, so this is something that is under development, but not for these kind of applications. We'll see. If you can't do that, compare it against something else where you know what you have. You define a null model or a null experiment. You leave out something where you know there could be some kind of influencing factor. So we have no idea what a critical transition is. We have no idea how long it is. Is it a period? If it's an event, we have no idea what it is. Yeah, we are searching for something. What do we leave out? Okay, start with something that allows you to do. If you want to have some kind of just detection, you use a random predictor, the Poisson process. You just claim that there was some kind of a detection in some random way. If you take into account fluctuations, then you would need to do Monte Carlo simulations. I show you 3 examples or 2 examples of that. Then you will see that you can get more information about that. But again, this is statistics sitting on statistics, sitting on statistics, sitting on statistics, sitting on time series analysis, sitting on data. Good. You spot on process. Yeah. You generate the detections or predictions at random times. Can be done, and then you compare. You use the same rate as what you have with your method that you have identified. So you adjust the rate of Poisson process, and then you're done. You can use some kind of adjustments that come from near periodicity artifacts, if you have something like that. And this is the reason why it's mostly used, because it's easy, it is fast, and it's easy to understand. And this is the reason why people do stuff, because it's easy. If you have some fluctuations that we have seen, then you would compare this against a random predictor. Who will win? You don't need to plug it in. Who will win? Just by what would you can you imagine who will win? The random predictor or the other? The one that you have. You do the same again. Yeah, you just explain that, or you just claim that there have been events, and you do again receiver operating characteristics, and you compare two ROC values. Which one will be better? If you have fluctuations that are driven by something. The original is better. There is no randomness because you have already some kind of structure in the data. Also in the structure of the sequence of events, in the structure of the occurrence of some kind of critical events. Yeah, if you have that, don't use that. Might be as a first guess, yeah, but don't go for any other things. So you would need to go for Monte Carlo simulations. Typical example. Yeah, I have no idea how I can modify CERN, so I run a Monte Carlo simulation on that. I have enough computer power. Why not do it? Yeah. You change the detector, you change that one, you change that one, then you find a new particle. Why not? Now, then let the experimentalist prove if this is correct what you have found. Here are some ideas that we have already put forward more than 20 years ago. Yeah. The first one is a random shifting of the occurrence times. Random under the it's a constrained randomization. Yeah. The original onset, original occurrence was here. And now you say, I generate, and then there's another one, and maybe another one. And then you say, randomly somewhere in between. But now comes the constraint. I know that some driving force, external, internal, whatever, makes some kind of quasi-periodicity. Take that into account. That means the distance between the occurrences needs to be fixed. Yeah, so you choose, depending on how many periodicities you have, you choose randomly from some distributions in order to randomly choose a new fake time. Yeah, and then you do exactly the same again. Or you randomize the time series that you have for all these fluctuations that you have seen. Again, under some constraints. I will show you some examples. Yeah. This is much more intensive computationally, and you would need to know how many of these randomizations do you really need. So that requires some null hypothesis testing. You need to set up again the good null hypothesis, which could probably explain what you are doing. Null hypothesis for the first one here, the critical transition is abrupt phenomenon. Intermediate transitory phase or precursor does not exist. You do exactly the opposite. No other constraints. This is simple. Yeah. We go away from fluctuations that we see. Here's an event, here's an event, here's an event, here. This is the sequence of the original sequence of events. Yeah. The surrogates that are being generated is now something to the sequence number 1, sequence number 2, 3, 4, and so on. Yeah. And then you do exactly the same again. You have the ROC values for the original one. You do the same for each surrogate sequence. And then you compare that. Comparison, it's not just comparing them outside or inside the distribution. You can, of course, ask, how many surrogates do I need here? Yeah, then it's an issue of what kind of statistic you need. There are robust test statistics, not just simple t-test or whatever. Yeah, but you do some kind of non-Gaussian test, and that would define the nominal size of the test. Yeah, if you assume that you allow error of 5%, uncertainty of 5%, that would mean you need to generate 19 surrogates. 19 plus the original one is 20. Yeah. That is depending on what you do. Yeah. If you would want to have something with a higher reliability, if you believe in statistics, and you go for 0.005, generate as much as surrogates as possible. Possible means don't generate these new surrogate sequences need to be independent. You can, of course, set up a surrogate sequence where each and every data point is always the surrogate of the previous one.
Klaus, sorry, and how can we be sure that your null model is correct?
It's the null model. This is infinity minus 1. I'm not talking about correctness. It's a statistical test. Yeah. The alternative hypothesis. This is the universe. And this is included in the other ones. Yeah. It depends on how you define your null. Yeah. Yeah. Elementary. Yeah, you can extend it if you want. If you do that, then you come back again to what I showed you before. These are the reddish ones. Yeah. So that means if you have an ROC value that is not necessarily the highest, but it can pass such a test, this is more reliable than only sitting on an ROC value. And the only claim I have the highest ROC value means nothing. This helps you, Mario, this helps you to single out some of these approaches. Yeah? It does not necessarily mean that if you now say, okay, if I look at the bivariate techniques, and then I know it's this kind of synchronization or that form of synchronization, that this is now, that explains the world. Yeah, not like that. Yeah, but it gives you a little bit more confidence or that could help going in that direction.
And what do you think about, instead of considering a null model, I mean, more the generation, the surrogate generation correspond to a null model, but instead of considering that, consider the opposite, for instance, resampling your data in order only to compensate the disbalance of the data, of the distribution.
And resampling.
Yes.
This is resampling.
No, resampling, but without considering any null model. I mean, only
Without null model.
or for instance, subsampling of the majority class in order to balance the data.
Why not? In terms of the not well populated distribution of them, yeah. That is the faking of onset times is basically something happened. Yeah, because you don't touch upon the rest. Yeah, but the opposite one. Bitte.
Yeah, I want to know how you, I mean, when you look at the distribution of pre-seizure data. Okay, someone had told you where are all the seizures, you're looking at your beautiful EEGs there, and then you, around each of them, you go along and you say, oh, there are some pre-seizures. So how do you decide what is a pre-seizure and where it is? How do you decide?
I don't.
What is a pre-seizure? And so then you can start working around,
Okay.
but you have to know what
Okay.
is a pre-seizure.
Okay, this is what I mentioned here with all the assumptions. If you take, irrespective of what you are doing here, yeah, if you take this plot again, yeah. So somebody claimed, in that case we claimed,
Yeah.
that there's a decrease in the phase synchronization prior to the seizure. So I would expect in some time frame prior to the seizure that there I see a decrease in synchronization. I will claim then that this is the pre-seizure.
Okay,
assumption. Yeah, this is that we have no idea what it is. Yeah, you take it from the data, you see some change prior, then you say this is indicative for that. But how often do you see a decrease in synchronization?
Yeah, okay, that is a good.
All the time, of
So,
course. Yeah,
but
so
that's why, I mean, besides, I mean, it's not a very effective method if you want to use it to the patient.
yes,
Because
you're not yet. This is
okay.
literally online.
Yeah.
Yeah,
Uh-huh.
this is just retrospective learning
Yeah,
of
okay.
what could be
Yeah,
a transitory phase or a critical phase.
Yeah.
We're not at the point. Yeah, I come back to this at the end.
yeah,
I'm almost done. This is, yeah, you sample one distribution, not well calculated, but you fill it up. You can also do another way. And then you say, you keep the times fixed, you go for the other distribution, and now you shuffle that. Yeah. So the applied time, the null hypothesis is now the applied time series is not suited for a detection of a critical transition. Yeah. You try to single out that one. What you have done does not work. So why does it work? Now you need to go for some kind of a constrained randomization of this new time series of your measure that you have extracted from the data to decide, does this help or not? So same again. You test the null hypothesis for the non-existence of a transitory phase. Exactly reverse. Everything else goes into the other hypothesis, into the higher classes. Yeah. There is no assumption about some static or dynamical model of the phase development. Now, if we go again for phase synchronization, we have no idea what this is. There is a transitory phase. We have no idea what this is. It could be static, it could be dynamical, it could fluctuate. It doesn't matter what it is. Yeah, you just say, let there be something. And then you do a constrained randomization in order to again generate a surrogate time series of your profile that you have. Yeah. This is now, and this is why it's costly. This is done by simulated annealing. Now it's up to you how many computation time you want to spend and how much power you have. You can put everything. This is jackknife. Yeah, put everything in what you would like to do. Yeah. Again, if you do, you need to compare then again the data, the findings that you have for the surrogates. You need to compare this with the original one. If you allow for a 5% error, yeah, you need to have again generation of 19 of the surrogates. Be aware, sequences must be independent. This is the risky thing here. Yeah, if you do simulated annealing, it could mean that you generate 19 times the same surrogate. Yeah. Be aware that this does not happen. So then preserve the original sequences of the occurrences if you want that. You can also destroy that if you want to go for that. And then if you find something, then the ROC or the AUC that you get for these sequences must be higher for the original one. So you need to be just outside of this distribution. Okay, some reference to simulated annealing. You know what simulated annealing is. Have you heard about that? I showed you one of these time series as an example. This is how they all look like if you take all of them into account. Yeah, so you see that there is some kind of anti-correlated behavior sometimes, and the rest shows some fluctuations. There are some fluctuations where you don't see this large fluctuation sometimes. Why the hell in the brain do you not observe an impact of the circadian rhythm everywhere? The sun is outside, it's far away. Why does it affect that brain region but not that one here? Not clear. So this is the raw data. Now you look at the distributions that you get from the simulated annealing. you see what happens. Yeah. Sometimes you have unimodal distributions, sometimes you have multimodal distributions. Mhm. Now you need to make up your mind of how to distinguish them. Yeah. Again, another issue that pops up then, and that is then due to the effect that if you have some fluctuations that go high and some go low, and that repeats itself, and of course you end up with bimodal distributions. Yeah. And if you have other kinds of driving forces in the background, you might end up with non-discrete or discrete values that effectively sum up into one unimodal distribution. Anything can happen. If you look at one, if you take these profiles that I showed you before, that one here. Yeah. So this is data sampled over 6 days continuously. Then you look at the cross correlation function of these times, of these new time series, and then you see that there is one here at around 1 day. This is the circadian rhythm that pops up. Yeah, so you will need to choose in order to reproduce that. This is something that you would need to have it as a constraint. Yeah, you typically, if you just do some kind of simulated deleting, you will not see that. So you will need to put this into some cost function that you retain the autocorrelation function, such that you have now a new surrogate time series that also includes these kind of fluctuations that you have. And that's specifically for each and every recording site. This is the next problem, or the brain regions that you're looking for. That is the reason why I don't answer your question, because there is nothing that is general. Okay, you need to define a cost function, then you need to do the minimization of this cost function for all of the permutations that you said. You need to have some kind of an iterative scheme such that whenever you increase the temperature, if you stuck in some minimum, you kick it out again, and then you try to cool this down until you have some kind of temperature that is used here. So this is the deviation of this cost function from something that you define as a desired accuracy. Other things that you would need to take into account. Sometimes you have gaps in the recordings. Do you want to have these gaps retained? Do you want to have them at the same position because it was a recording gap for this new surrogate? Screen sharing stopped. Why?
I will to call it.
Okay, I have it.
You got it?
Good. Sorry for that. I know I'm almost done. Just some examples of how that would look like. Yeah. So you have this is the original sequence on top, and these are now surrogate sequences of exactly that what the scheme behind it in order to produce this one. So you have the same gaps here, you have the same type of long range, short range fluctuations. The times where something happened is of course the same because we didn't touch upon that. Can combine that if you want, yeah, but that would be just one of the schemes to do that. And the reddish one are the original ones, the others are the 19 surrogates. So find something where the surrogates are outside. Here, it's here, it's here, it's here, it's here, it's here. The rest is inside the distribution. So with that, you have singled out some of these time series where you have an indication for a pre-seizure state. Yeah. Based on something. That's it. Good. One aspect that you will need to take into account. These are only statistical tests. They don't prove the existence of a critical transitory phase. Now, if we continue with that, yeah, you say, okay, this is not a good sample, this is not it's badly sampled, we do this, we combine that. Again, you end up with assumptions that are sitting on assumptions, in order to single something out. Yeah. Of course, you can make it better. Yeah. But the question is doing something better really helpful here? Yeah. In that case, it's just an indication. It does not prove correctness. Nothing else. Yeah. And then take into account, you reject the null hypothesis. The null. The universe is in the other ones. Yeah. If you know that there are other factors, you can of course include this into the null and make then the surrogate concept better. Yeah. This is just the beginning. You can continue with that and then make better null models for that and better surrogates for that. Yeah. So we have mostly statistical approaches. This lecture was on time series analysis. Everything is based on some statistics because we don't have the models. We don't know what it is. We don't know what are the underlying mechanisms for that. We would like to identify, is there something that we can extract from observations such that we have an idea about what is the mechanism for a critical transition? You need to interpret that. And what you would probably put is highly recommended is avoid wishful thinking that it's. It must be like that. Somebody said, and Enrique said this, so I must be something in that direction. And now I have it. Yeah. No, you don't have it. Most of these techniques, what I showed you, only work for by location-induced tipping. One-dimensional systems. Not that famous. What about others? I know that some people are working on that, try to identify other indicators for different types of transitions. You will need to identify that also then from time series. And then the question of how to do that. Yeah. Some of these time series analysis techniques that might give you some clues about that, yeah, but not more. And this is what I would show here, that there must be much more interactions between theory and experiment, because in the theoretical world, there is so much there. But the experimentalist would need to know what is there and how to adopt their measurement techniques in order to get some better findings. And of course, you would need then also improve then from that side sampling and other aspects.
I think we should finish.
I'm almost done. Yeah, almost done. There is more on that side. This is model-based, yeah, but there is nothing available so far. And all these data-driven aspects that goes into prediction. Yeah, this is now the next point. How to do that? How can we possibly do that? And here we end up, of course, with unsupervised, supervised learning techniques. What can be done? You see, there's lots of techniques available, but at the end, yeah, you end up with your machine learning technique tells you can distinguish something. You can distinguish something. It does not tell you anything about the underlying mechanisms. This is the problem. Yeah. So this is my last slide. Yeah, if you do that, yeah. You need it either as white box or black box. The question is, what does it really help you if you use these approaches? And then, if you use, even if you go into the explainable guys, you sit an AI onto another AI onto another AI that tells you that some factor somewhere or some number has changed. What does this mean? The interpretation, this is the critical problems that if you want to go in the direction of understanding critical transitions. Now I'm done. Thank you. I would suggest. I don't know what time we have. I'm definitely over
The
time.
point is that we have a service on coffee break
Yes.
outside, but I mean, you can continue in the
We can
afternoon.
continue in the afternoon. We have now a coffee break because it was much too long and Ulrike needs to go for the next door. And then we need to stay.
Right now, we
Yeah.
are-
Okay, good, thank you.
Sorry.